Um, Hi everyone, I'm Yuan. Today I will present our collaboration work, Heliostat, harnessing ray tracing accelerator for page shape walks. This is a joint work between UC Merced and Yonsei University. Modern GPUs are becoming ultra heterogeneous. We have CUDA cores for vector computation. We have matrix cores for tensor computation. And more recently, we have ray tracing cores for accelerating real-time ray tracing workloads for graphics. And as shown in this fancy picture, ray tracing is a technique to render vivid light bounces and reflections in a scene. But firstly, why we need a dedicated accelerator for this? Firstly, real-time graphics latency sensitive, while ray tracing is a time-consuming operation. What it does is that suppose we have a 2D scene, and we wish to trace the path of a light or a ray. A modern algorithm is to decompose the scene by bounding boxes and build a tree structure, we call it BVH, based on the position of the primitives. Then to trace the ray, what we do is that we trace the tree instead of the original scene, and the target is that we want to find the closest hit over all the primitives. As you also noticed, if in a game that there's millions of rays are bouncing in a scene, then massive memory level parallelism is required. But unfortunately, such irregular traversal fits poorly with SIMT architecture and performance model of the modern GPUs. Therefore, to meet the needs of advanced rendering, GPU vendors choose to add dedicated accelerator to accelerate the traversal of BVH. However, when GPU application is running and there's no RT graphics workloads is running, the RT accelerator remains underutilized. While the GPU are becoming heterogeneous, another trend in GPU is that the GPU memory bandwidth is scaling up due to the needs of emerging applications like LLM and genome analysis. In this figure, we show the memory bandwidth of the GPU models from 2010 to 2024. Over the last 15 years, the memory bandwidth is increased by over 30 times. However, to access a virtualized memory, we have to firstly translate to physical space. Here we ask a question: can the bandwidth of virtual memory system catch up the scaling of memory bandwidth? To investigate this, we conduct our motivational exams. And here is the architecture that we target at. So in one GPU, there are multiple shader arrays and multiple compute units in the shader array. And in each compute units, there is one matrix core for GEM operation. And lastly, there is an RT core per CU for ray tracing accelerations. We consider a hierarchical virtual memory system that there are multiple levels TLBs, and for GMMU, which is GPU MMU, we consider highly threaded page table workers to traverse the page table radix tree. We firstly conduct experiments on performance when different number of page table workers is used. In this figure, we can observe that when we hypothetically increase the number of page table workers from 16 to 128, there is a significant performance improvement for those memory intensive applications. However, it is not easy or always scalable to increase the number of page table workers, as they also introduce power and error overhead. We then break down the latency of the page table walking. In this figure, the light gray boxes is the time that a translation spent on waiting for unavailable page table workers in GMMU. This means that the parallelism is not enough for GMMU, and there is a huge mismatch between the bandwidth of memory and the bandwidth of virtual memory system. But wait, if we compare the page table walks and RT accelerator, we will find that the page table walkers traverse page table radix tree, and the RT accelerator traverse BVH, essentially a tree. And then page table walkers is able to provide some level of parallelism, but pretty limited, while the RTA is designed to leverage the huge memory level parallelism exposed by the modern memory systems. And finally, we just proved that the GMMU is require more bandwidth under modern GPU setting and emerging workloads, while the RTA is underutilized when there is no RT application running, which is often the case with GPU application. We then can have our own idea. That is, we bring our goal. We want to fill the parallelism gap between memory and the virtual memory systems. And our key idea is that we propose to leverage the parallelism and repurpose the underutilized RT accelerator for page table walks. To this end, we introduce Heliostat, which consists baseline Heliostat and Heliostat Plus. So in this figure, we show how the baseline architecture or pipeline of RT accelerators. Here, suppose that we have submitted ray tracing tasks, and the traversal threads are organized in the warp buffer. And for every cycle, the warp scheduler will choose one or several warps from the warp buffer and try to issue them, just like warp issue scheduler in CUDA cores. Then the ray will be decoded, and the node decoder then reach the OP destination table, where the node type is actually dedicated to BVH building algorithm that is dependent on vendors. And for non-root nodes, the raybox intercept task will be performed, and after the test, the traversal stack will be updated, and the traversal memory transaction will be also scheduled. This traversal will be triggered recursively until it finds the closest hit, which is in a leaf node. And then the intersection task will be done between the ray and the primitives. This process will also be performed recursively until we find the closest hit primitive. Well, we propose to repurpose the RTA. The repurposing RTA accelerator is not, for page table work, is not easy. We have three major challenges. Firstly, as we just discussed, the pipeline of our RTA accelerator are highly customized and dedicated to retracing workloads. So does the tree node format. Secondly, since RTA is a functional unit of CU, just like a tensor core, it can compete for cache resources with a regular memory transaction. And thirdly, it is not always optimum to always delegate the page translation to RTA and leave the GMMU to idle. We need an arbiter to distribute the translation tasks. Let's start with the first problem. Firstly, let's see how we modify the RTA to perform the page table radix tree traversal with Heliostat-enabled RTA. A conventional simplified BVH internal node is as shown here, as shown before as well. Conceptually, what we want is that we want to map the radix tree nodes to be the tree nodes in the BVH. And we want to map the virtual memory translation request to be the ray in the ray tracing. So firstly, we extend the nodes decoder and also the OP destination table to be able to decode the process, the node to process the standard page table entry format. We then extend the ray property field from the current format, which is 3D geometric specific, to a format that is fully compatible with page table works, in which it consists of all the essential fields to perform page table works, including virtual addresses, PID, access control metadata, and the level of current radix tree work. Since the packet size is smaller, we don't have to extra packetizing. We also modify the OP destination table to recognize the page walking ray and redirect it to our newly introduced page decoding unit, PDU. PDU is a simple execution unit, just like ray triangle intersection units. It is used to decode the returned PTEs. All the essential functionalities like page translation, access control, and customized page fault handling is included. Please check our paper for more detailed implementation. We now solve the first challenge, and then let me introduce how we solve the cache resources contention problem. We first observe that in modern GPUs, the scalar cache is also underutilized. The scalar cache is mostly used for constant values like shared pointer or shading resources, and since they are shared by the whole shader array, we are able to share them between CUs within the same shader array. We benchmark and quantify the utilization rate of the tested benchmark, and the average utilization rate is only 4.3%. So we propose to modify the scalar cache controller and specialize one way out of each set to store the tree nodes of page table. This way, the cache resources contention can be minimized. Finally, to dynamically decide which unit should serve the translation request, we introduce RT page table walk forwarding unit, which is located by the side of shared L2TLB. The structure of RFU is very simple, and it's periodically check the availability of page table workers, and only when it monitors that the GMMU to be busy, it will redirect the page table translation request from L2TLB to the original initiator CU. We then solve all the three challenges. Now we've discussed the architecture change of Heliostat. Let me show and work through example here. Suppose that we have an L1 TLB miss that will be delivered to L2 TLB, and it reached the L2 TLB, then let's suppose it's also the miss. But instead of directly sending it to GMMU for translation, we will first send it to RFU. Then the RFU will check the availability of GMMU page table workers, If the page table workers are available, then the request will be sent to GMMU. However, for this example, let's consider the GMMU is busy, and the RFU will send the translation request to the requester CU. The RTA in the requester CU will receive the translation request and regard it as a special array that traverses the page table radix tree instead of the BVH. We will firstly check the local L1 scheduler cache for intermediate nodes for multiple levels. Upon L1 scheduler cache miss, you will instead traverse the page table radix tree that is located in the memory. After multiple level of page table radix tree is traversed, the translation can be finished and refill the L2 TLB. Now we discuss the idea behind Heliostat and how RTA can be used to serve the virtual memory translation request. However, we have not unleashed the full potential of RTA. Now let's consider a rendering case that I wish to render a frame in a given scene. We want to trace if there is a given ray that is able to reach our camera. We then shoot the array from our camera, and towards the scene, the ray hits a glossy surface. The ray will go through the glossy surface via refraction. But other than that, the reflection also happens on the surface. Another ray should be evoked and also traced. Modern RT course is able to trace a secondary ray via certain APIs like Vulkan without a problem, thanks to its massive memory level parallelism. Interestingly, we find interesting behavior and unique opportunities in page table works. Where we have the rule nodes, which is 0-3 register, and for each level, we extract the bits and traverse the children PTEs. This way, we are able to finish the on-demand translation. To this end, we consider if we are able to observe that there is a common thread between the two translations, and we are able to leverage the secondary spawn. Here, we borrow the idea and the functionality of the secondary array and propose Heliostat Plus. That is, a translation request can carry another look-ahead translation where partial of the traversal path is shared, and only when the traversal path is forked, as shown here, the look-ahead translation can directly start the traversal from an intermediate nodes. Here, we name it as a look-ahead translation. To enable the look-ahead translation, we further modify the architecture of baseline Heliostat. Firstly, the ability of handling secondary array is usually done with dedicated shader codes. In Heliostat Plus, we propose PDU Plus, where we enable it with the ability to invoke a secondary array and a lightweight hardware units to calculate the address of look-ahead. Secondly, in the RT PTW forwarding units, RFU, we include a stride monitoring units to monitor the miss translation in L2 TLB. It will dynamically observe the stride, and the observed stride will be included in the translation request. And furthermore, we include another hardware-efficient cuckoo filter to note and memorize whether an address has been fetched before via look-ahead. Thirdly, we further leverage and repurpose the L1 scheduler cache as a storage buffer for look-ahead translation to not pollute the TLBs and minimize the contention with on-demand translation. Let me show an example here. Suppose that we have a miss in shader array A, and the miss will be forwarded to L2 TLB. Suppose that this is also the miss. Then you will go to RFU Plus. When GMMU is busy, then RFU will forward the translation request to the original requester along with the most common observed stride. The RTA in shader array will translate both the on-demand translation and the look-ahead translation. The on-demand translation will be refilled to L2 TLB, and the look-ahead translation will be also registered in the RFU Plus. Then suppose that in shader array B, we have an L1 TLB miss as well, and the address is the one that shader array just look-ahead fetched. Then the request will arrive at L2 TLB and the RFU Plus if L2 TLB is a miss. Then RFU will look up its cuckoo filter, and the cuckoo filter will likely to report that we have a translated copy. And then the request will then be redirected to shader array A and look up at its L1 scheduler cache. Then the translation can be finished without actually looking for a traverse the page table radix tree. Finally, let me introduce our evaluation. We use cycle level simulator and GPU sim. We consider AMD GCN3 like ISA and GPU model. where there are 128 compute units. We have implemented the functionality of tree traversal in RTA. By following previous works, we basically model it similar to our low-throw units. And there is one RTA per CU and 4 set of optional units, and we allow up to 4 concurrent warps. For virtual memory system, we use 16 shared page workers and 128 page working queue, 120 shared page working cache, similar to previous works. Now here we show the performance impact with Heliostat. On average, Heliostat is able to achieve 1.66 speedup over the previous state of the art. And if we enable the lookup translation, Heliostat Plus is able to further outperform based on Heliostat by 1.23. In this slide, we show the average translation latency reduction. On average, Heliostat is able to reduce translation latency by 41%, and Heliostat Plus is able to further reduce the latency by 17%. We have many other evaluation results, like performance breakdowns, performance under page migrations, and much more. Please check our paper for more details. Thank you.